All right, folks, have a seat and now we get started. So super excited to kick off our FAI speaker series for the fall semester. So today we have our first speaker, Professor Rob Platt. So Rob is a professor from Northeastern, and he's also a faculty fellow at BDI or BDII. So I believe it stands for Boston Dynamics AI Institute. Is that right? So what do you guys call yourself? Like, I also see B in AI Institute.
Yeah, I know. I think that they want to change the name, but they don't have permission.
Okay, BDII, right? So, and Rob used to be a postdoc at MIT, and he is also like a technical lead at NASA. So he did all the cool works and with RobotNet 2, the first humanoid robot in space, and also involving the Valkyrie effort as well there. And he has some kind of connections with Texas, right? So he stayed in Houston with NASA for 4 years before he became a professor in Northeastern. So what I particularly like Rob's work is how he was able to combine the domain knowledge of robotic structures and from robot dynamics and control into the learning system to make the robot learning algorithm more robust and more data efficient. And today we're going to see learn about his work on using symmetry, right? So in policy learning. So with that, so
all right.
Rob, yeah,
thank you so much for the kind words.
Yeah, and yeah, floor is yours.
Great. All right. Hello, I'm Rob Platt. I'm at Northeastern. I'm also co-leading a team with Steffi Telex at Boston Dynamics AI Institute. The content of this talk is just on the Northeastern stuff. So that's but we're doing lots of cool stuff with BB. So the focus of our team is on skill learning and skill composition. So I'm happy to talk about that another time. Great. So we have a problem in robotics, and its name is data. The machine learning models we use, I imagine you all know this, require lots and lots of data to train. I have to say, please interrupt with questions. I'm happy to do that. And also, I really appreciate you guys being here, given that there's an ICRA deadline like the day after tomorrow or something. Okay, you need lots of data to train these machine learning models. That's a problem. It usually ends up with folks being asked to provide lots of demonstrations of ridiculously simple household tasks like this. I don't know what these people did to warrant this kind of punishment, but it seems like hopefully the punishment fits a crime. It seems like something out of Dante's Inferno, a level of punishment suitable, maybe just above the level of heretics. Yeah, so collecting physical robot training data is hard. Whether you're doing reinforcement learning and your robot needs to spend a lot of time like just bobbling around the environment, doing whatever it's doing, collecting that learning data, or whether it's learning from demonstration where you're in the situation where you're condemned to provide lots and lots of demonstrations of silly tasks to the robot. So yeah, so you might say, well, Rob, don't you know that there are efforts underway right now to gather large amounts of training data to solve this problem? Because truly, it is the case that our models do require lots of data, but we can collect that data. And I guess I would just point out that the effort to put together a multi-institution effort to collect lots of data on lots of different platforms, that's not nothing. And furthermore, to use a data set like this involves solving a significant domain shift issue amongst those. You might need to use data from robots that are different than your own. And really, you only have a lot of data for a small number of tasks. And you'd need to transfer that task knowledge to whatever task you're trying to learn about. Maybe we should train in simulation. It's much easier to collect data in simulation, as you probably know. But of course, this still leaves us with a significant domain shift issue. And furthermore, I just point out, like, anyone working in simulation is at the mercy of unmodeled variation in the environment. I mean, it goes without saying, but if it's not in your simulator, your robot doesn't know about it. Another avenue toward obtaining the data that our models need is human data. I like this. This is a great one. Let's mine the internet, get lots of human data. Again, the challenge here is solving a significant domain shift issue, a domain shift between the domain in which human data exists, which is humans doing stuff, and your target domain, which is, of course, the robot. And I guess, like, the way I see it, the real problem is robotics folks are using a bunch of models that were developed to solve computer vision and NLP problems. Those are domains where data is plentiful. That's not our situation. Robotics, I propose to you that robotics needs different models different than the ones that the computer vision and the NLP people are using. They're more data efficient, more suitable for learning from the relatively small amount of experience that our robots have. It's not to say that we don't want to use NLP, priors from computer vision and NLP, but I think we need to think harder about the models that we're using. So this talk, I'm gonna propose what I think is an interesting direction there, which is to incorporate domain symmetry into the structure of the neural network. In particular, we use something called equivariant neural network layers, and I'll talk much more about that. But essentially, I'm going to propose that we identify by hand, hopefully we can find ways to automate this, but identify structure that exists in the domain, bake it into the neural network, hard-code it into the neural network, and improve data efficiency that way. And I think that this, that idea is something that folks in the robotics community have been trying to accomplish for a long time. And I think we don't know how to do it right. I think we tried different things and they haven't worked very well. And I think equivariant models work unreasonable. They work surprisingly well. That's what I'm going to try to tell you about today. Before I get there, I want to just put this in context. I mean, I've been working in robotics for a while. And about 10 years ago, we were in this world, the small data world. I don't know, the model-based world. About 10 years ago, except for Peter Stone, who's always been doing RL. Robotics was in a model-based world, basically incorporating hugely powerful priors that require only a small amount of additional parameterization. And there's a lot to be said for this. You incorporate big models, you structure your computational system, your reasoning system, and there's, you can do really powerful planning here. I don't know, maybe this goes without saying, but the weakness here is that these models incorporated a lot of assumptions, too many assumptions that were easily broken in physical environments. And as a result, these models were very brittle. They broke easily. And as evidence of that, you look at robot videos for something like 10 or 15 years ago, you see robots trying to pick stuff up, and it's, they'll be like knocking over objects. You'll see robots like try to pick something up, they'll close on air and be like, and they'll go through the motions like they're not even aware that anything happened. The other side of this, of course, this is us right now, the big data regime. It's like the duel of where we were. There's no model, or very little model. The only model we have is a neural network. God knows what's going on there. And then we compensate for that lack of structure with lots of training data. And obviously, what I'm going to pitch to you today is the thing that lies directly between these two extremes. We still want to adapt based on experiences from the real world, but we want to try to incorporate as much knowledge, prior knowledge as we can. And figuring, and it seems like just based empirically, like on what the field's been doing, it seems like the challenge is figuring out how to incorporate structural priors, model-based information into the model and still learn effectively. Okay, so let's get to it. I'm going to describe a ridiculously simple type of structure that is often present in robotics problems, and that is going to be surprisingly helpful. And this is rotation symmetry. So here we have this manipulation problem. Imagine that this infinite plane here is really a tabletop, and we have like some object here on the tabletop that we're pushing. Okay. So this is the behavior, and I want you to look at the left-hand side of the screen and the right-hand side of the screen. So on the left-hand side of the screen, we're seeing this transition of pushing the block kind of toward the audience. And on the right, we see the transition of pushing the block toward the right side. And you know, I want to point out that these are the same transition actually modulo a rotation of 90 degrees. So the transition dynamics that under like the friction and the contact dynamics, the things going on the left side is exactly the same as the things going on over here. They're just transformed by a 90-degree rotation. And that's what, so here we are, SO2, the space of planar rotations. These are rotations about the axis pointing out of the table. So, you know, rotations in the table, like we see here. Yeah, all right, and a bit of notation here. So S is obviously state, when we compose state with this G is the group element. I'm actually cutting a little fast. The G is actually the action of the rotation on S. So it's like the rotation of S being, and let's say that S is an image, top-down image of this environment. Doesn't have to be, but just bear with me. Right, and then S prime is the next state and action and whatnot. All right. Yeah, question.
Can you clarify what you mean by like what's in the state here and what's not?
State,
It doesn't seem
imagine
like
it's
the arm
imagine that
itself
it's
is just being
oh
rotated.
that's great. That's great. Yeah, that's really good. I'm sorry. Yeah, imagine that it's just the object and not the arm. Yeah, imagine that we factored out the arm. And you ask me about if you want, ask me about that later when when we actually do have the arm in there, and it's like, how did that work? All right. Yeah, so that sameness of the left and the right-hand side of the screen that we're just talking about, it can be summarized by this equality at the bottom of the screen. So this is essentially an invariance constraint on the on these dynamics to rotation. So here we have the probability of S prime, the next state, given that you take action A from state X, S. This is how, I guess you guys are computer science. This is how computer science people write transition dynamics. So this is the transition probability, and it's invariant under rotation, under the rotation G. That's what this equation is saying. So we're saying that we have a domain that has this structure where, let's say, G is a planar rotation. What we're going to do in a moment is we're going to leverage that structure to speed up learning. All right. Yeah.
So from this slide and the one you said before, it sounds like the way you're going to speed up learning is by putting some constraints into the model itself.
That's right.
There's, from a very high level perspective, there's the completely other way of keeping the model free, but doing data augmentation, and every piece of data, you flip it and rotate it.
That's
so
good.
You just send it in. So,
yeah,
so
you could do either one of those.
Okay.
Yeah. But our method works better.
Okay.
Okay. Yeah, and they're not exclusive either. Like, you know, I guess you'd want to do both. Yeah.
I guess one comment sort of related to what Brad was saying is that like the G of A here is doing a lot of work, right? Because you're sort of assuming that that there is an equivalent action at any rotation for a given, you know.
Yeah.
Yeah.
You're defining, you're saying there's a group out there and you know how that group operate, elements of that group operate in the state space and the action space. So here in this domain, it's pretty straightforward because, you know, if this is a velocity in the plane, then obviously we can rotate that. But that it's, you know, you're incorporating some degree of domain knowledge here, and it may not always be evident.
Right, but like if it's an arm, you know, then it might be hard to.
That's right. The arm would be a symmetry breaking thing. That's going to reduce performance relative to this perfect scenario. Turns out it's still very helpful to use these ideas. We'll get to that much later in the talk. Yeah. All right, it's different. All right. So just this is an important point to make. So far, I talked about the fact that it's often that, well, you might have structure in the domain. Well, how does that help us? Well, structure in the domain in the transition function implies that optimal value function, the optimal policy are also going to be structured. So the optimal Q function is also going to be invariant, and the optimal policy here is going to be, this equality here is an equivariance constraint. I'll tell you about in a moment. So this is actually, it's not too hard to prove this. This thing can be proved by induction on the Bellman equation, which is something we did, but it's also, you know, there's like old results in RL from a good friend of mine, who you know, so this idea has actually been is a special case of ideas that have been known for a long time. Just want to point that out. All right, so far so good. So when the domain has symmetry, then the optimal solutions have symmetry. We're going to bake the symmetry into the neural networks that we're using to approximate these things in our actor and critic, let's say, and things are going to get better. Let me speak for a brief moment about what it means to have an equivariance constraint. So here we have, this is image segmentation. So we have an image, F is the segmenter, generates a segmentation. Notice that this equality is satisfied here for a correctly operating image segmentation function. You should, a good image segmentation function, you should be able to segment the image and then rotate the segmentation, or rotate the image and then segment the rotation. Those should produce the same thing. That's not the case for an arbitrary function f, but if you know something about the structure of the segmentation function, which we do, you could bake this into your function f and maybe help yourself out. Actually, let me. All right, yeah. So okay, so now I want to talk about just. Yeah, I'm not going to talk a lot about the innards of the equivariant neural network. Yeah, the next question is, okay, we've identified the constraints. How do we bake those constraints into the neural network? I'm going to talk about a simple instance of how that works. This kind of has a variety of different instantiations, but I think this is a good place to start. So again, we've got the rotation group, the planar rotations, SO2. And we're going to discretize it. So instead of the continuous planar rotations, we're going to have a discrete set of rotations, rotations every 90 degrees. Right, that makes sense. And I guess in abstract algebra, you'd call this a finite subgroup of SO2. Is actually something called the C4, the cyclic group, the fourth cyclic group. All right, so we have this, we have this this rotation group C4, which is the set of rotations by 90 degrees. Easy, simple. So planar rotation can be represented in a few different ways. Maybe the easiest way is as an angle. You're probably also familiar with the representation of planar orientation as a rotation matrix. And and I don't know, you can also represent it as oh, I do have a picture. You can also represent rotation as if there's only 4 rotations, it can be like the vertices on a square. So each of those 4 vertices representing one of those 4 elements in that C4 group. So we have different representations. It is a little arcane. I know we have different but it's important. I have to talk about representation of the orientation because the representation is going to be inside of the neural network. That's why I'm doing this. So this is one representation of orientation, the standard representation, as it's called. And that represents the rotation matrix is actually it's an operator that performs the rotation, and I'm going to represent that as using the Greek letter rho, and rho 2 is just that's the standard representation. Now, if you're representing rotation as like a vertex on the square, then rotation is basically a one-hot vector because it's like because you're just at one of those different rotations, and then a rotation by, let's say, 90 degrees would be a permutation, actually a circular shift of those vertices, and you use this permutation matrix to accomplish that rotation. Okay, so again, this permutation matrix and that rotation matrix, they're the same thing in the sense that they're an operator which is performing the rotation on a particular representation. This thing over here is known as a regular representation, and it's the action in the regular representation is going to be represented by rho again. And this is rho 4, just because that's how we denote the regular representation. Okay. That was and I can't really proceed any further before telling you about Robin Walters, who's my collaborator in all this. You see, I don't know much about math, as it turns out, but Robin does. And it is because of him that I know anything about this, right? So it's fine. So sorry, Robin's faculty at Northeastern with me. All right, now let's talk about the neural network. So equivariance, we use equivariance in a variety of different neural network structures, and I'm just going to tell you about how this would play out in the context of a fully connected layer. Now, first of all, we want to construct neural networks that encode this equivariance constraint end to end. Our mechanism for doing that is going to be to construct equivariant layers. And if all the layers are equivariant, if all the layers satisfy this constraint, then of course the whole thing is going to end to end. And we're going to focus on a fully connected layer. So a fully connected layer, as you probably know, you can think about that as a matrix multiply followed by a nonlinearity. Okay, so you have at the beginning of your layer, you have like a vector, in some latent space. You multiply that vector by a matrix M. That matrix M, those are your weights and your biases. And then you pass it through a nonlinearity. So that's your inner product layer, okay? So that's what's going on, let's say here. So we have this input in R2, we have a 2-dimensional feature vector that's multiplied, goes to this 4-dimensional feature vector, and then there's a nonlinearity going to this 4-dimensional thing, okay? And of course, there's going to be a stack of these things, but I'm just going to focus on this little bit here.
There's a question online. So,
Thank you.
is there work on representing rotations using complex numbers? You talk about this too.
Yeah, I mean, like I said, I don't know much about math, but yes, of course, you can represent orientations using complex numbers. That doesn't really play into this. Yeah. Yeah. I mean, I don't know, yeah, there's probably a lot more to say there, but let me not say it, all right. So what I want to do now, I want to, like I was saying, focus in on this, on this layer. And I want to find a way to constrain the layer so that this constraint is always satisfied. What is this constraint? This is the equivariance constraint in a single layer. Let's look at that for a moment. So X is the input to the layer, which is here in R2. Rho is the action on that so the R2 is this rho 2 is going to be the action, the standard rotation 2x2 rotation matrix to rotate that vector. And then M2 is going to be the action of this matrix multiply. Okay. That should be equal to X multiplied by M and then rotate. So if we rotate and then apply M, we should get the same result as applying M and then rotating. That's the equivariance constraint that we saw in the segmentation example a few slides ago. So we want to, and on the last slide, I defined what rho 2 and rho 4 were. So now we're going to, we want to figure out how to implement this constraint and just in this linear layer, forget about the nonlinearity for a moment. And the answer is, we can do weight sharing. So you can do the analysis here and figure out what weight variation you're allowed to have in M subject to the constraint of this equation being satisfied. And the answer is this. So you've gone from a fully connected layer with 8 free parameters to something with 2 free parameters. You can easily verify that that's the correct matrix by just multiplying it out again. So just substituting, so I asserted that M2 would have to have this structure in order to satisfy this equation. And you could multiply it out if you do this, indeed, it's equal. Great. So I don't want to talk specifically about the nonlinearity, but there's basically a similar argument that happens there. We are going to take this idea and basically use it on a much larger scale. So what's not showing up in this simple, well, first of all, in the simple example, you can see that we reduced the number of parameters. We've gone from 8 down to 2. We have improved our ability to generalize over the dimensions where we're hard coding that generalization, namely these rotations. Anything learned in one rotation is going to generalize to each of those 3 other 90-degree orientations. Now, what's not shown here is, well, there's nothing about batch size. This is actually only for a single neuron value. So in order to incorporate equivariance, we're adding another channel to the neural network. So we would have, there's an additional feature dimension channel and an additional batch channel. So you have to kind of imagine that it kind of gets scaled up that way. But this idea that I'm spelling out with the weight sharing is exactly what happens inside of a fully connected layer, right? Is this idea, well, roughly, I realize it is a bit of an intuitive leap here, but I'm trying to give a sense for how this might be. Yeah.
Another online question from Kyle. He was asking if people try this weight sharing for like locomotion, but that's in joint space has been turned not too effective. Does it matter which space you apply the symmetry to, like a task space versus joint space? I think that's a great question. I would like to figure out how to use this in joint space. I think it's hard to identify what are the appropriate symmetries in joint space, but I think this is just your work is task space.
Yes, for the most part.
I mean, for locomotion, then it's like for quadruped locomotion, we've used symmetries in sort of the policy space to just assuming that whatever you do with the right.
There's like a bilateral symmetry,
and then constraining the policy space in exactly the same way. So like the reinforcement learning for quadruped locomotion 20 years ago used that symmetry constraint in the locomotion.
Yeah, I think like it's like so many things in AI, like it's very clear what we want to do. It's a question of how we get what the mechanism is. I want to argue for this weight sharing mechanism as an effective thing to do. Here's an illustration of the idea working in the context of a single convolutional layer. So we have a randomly initialized convolutional kernel, unconstrained. As we rotate the scene, it's kind of bumping. Now imagine we're trying to do object detection. We don't want the object detector to be varying depending upon the orientation of the input. So you would like to have a constraint, so here's the constrained convolutional layer, and it's stabilized over orientation. Another way to think about equivariance is like as a search, in terms of a search problem. In learning, we're trying to find the parameters of a good model, and equivariance is applying constraint, essentially reducing the search space. Okay, so I'm going to go into a whole bunch of examples of how my group has used this idea in robotics. But before I do, I want to say to you that you can use this idea in your work. It's conveniently orthogonal to just about everything that folks are doing out there. So Peter just mentioned like data augmentation. Like, yes, you could use this with data augmentation. And in fact, we always do. All right, this first thing I want to talk about so now I'm going to talk about a bunch of robotics applications, and maybe I'll do this somewhat fast. The first of these is going to be kind of going from simpler to more complex. The first of these is going to be planar grasping. So here we're doing some bin picking. Our input is going to be an image that looks something like this. So we have a depth map of the things in the bin, and we've superimposed the gripper into that depth map. The output is going to be an X, Y, theta pose. Okay, so we're going to have a neural network that consumes that visual input that I just pointed to, essentially a depth image like this, and it's going to output a desired grasp pose. All right, and we're going to use an equivariant model, and I won't go into the details. So we're going to frame this as a bandit problem. So we've got the neural network that operates, like I said. One way to train this thing is in a supervised manner. You collect a lot of images and a lot of good grasps, and you train it. So we're going to do it bandit-wise. So the neural network is going to be initialized randomly. We're going to start collecting data, and on each experience, each iteration of experience, we're going to call the neural network, ask where to grasp, then we're going to perform the grasp, and that'll be a piece of data that goes into the buffer and starts to be used to train this thing. Right? Makes sense? So we're going to and then after we perform the grasp, we'll evaluate whether it's a good grasp or not, and that's like a label. So it's like a binary. It's like, I guess, is a contextual bandit, and the output is the output is exposed. Okay. Yeah. So we did this, and constraining the model, like I said, and here's an illustration of what that learning process looks like. So you initialize with zero knowledge, random weights in the neural network, and you start grasping. And we're collecting only a small amount of data. Up to now, there's only been 100 attempts. And whatever knowledge we've gained, we put it into the buffer. We start training this model, and the model learns very quickly. This is like the simplest application of equivariance to robotics like you could possibly come up with, because we're in the plane. This is like a regular representation, discrete representation of orientation. But the point I'd like to make is that we can learn to grasp, with the random system gets a grasp success rate of about 25%. After about an hour of direct physical experience, we can grasp at about 85%. So this thing can learn, we have a contextual bandit that can learn to grasp purely with physical experiences within about an hour, which is super exciting.
I think your outcome is really interesting for sure, but what also caught my attention is the initiation. You start at a much higher success rate.
It's actually, so this line starts at 50, it starts around 25. The random system will succeed about 25% of the time. You know, and that's because like, well, the bin is kind of full of objects, so. Okay, yeah, random graphs are about 25%. And this thing, yeah, this is an hour, you know,
You do start at the same level.
all of these lines are, yeah, the uninitiated, if you were to run the uninitiated system without learning, there'd be a straight line about here. But yeah,
To clarify, you're considering 90-degree rotations to be equivalent, or any rotation.
okay, so the symmetry group is, so first of all, I think this is a C8 symmetry group, not a C4 symmetry group. Okay, so more orientations in the symmetry group. Second, the symmetry group, which constrains the model, doesn't necessarily define what the action space can be. So the action space can be more fine. It can make more fine distinctions about orientation it wants to use. It's just not symmetric over those. If that makes any sense.
You can ask offline.
So you didn't get, how many symmetries do you use in the problem?
Something like C8, about a discrete, a finite group with about eight elements. It helps a lot. It's surprisingly effective. Yeah.
From your analysis.
I'm not surprised if you don't believe me. But I have so many examples that it's going to be hard to ignore it. Yeah.
I'm trying to understand from the example before, it looked like every symmetry constraint reduces by 2 the amount of parameters.
I'm not,
correct?
I wouldn't say that. I don't know exactly what the rule is.
Okay,
But I'm
because
not
in the
willing to
example,
say
you
that.
were kind of like through the symmetry.
No, I see that. We went from 8 to 2 and it was a 4 unit group, but I wouldn't try to generalize that idea. But clearly the larger the symmetry group, the more helpful this is going to be, but you know, there's a point of diminishing returns. I don't know.
Is it, so just last question, is it here, so are all the networks equally large? But in your network, you apply symmetry constraints or?
Yeah, so well, the gold standard is to keep the same number of parameters, but we have even fewer free parameters. So so it's sort of, in a sense, we have many fewer free parameters than the baseline. Like regardless of how you set these parameters, we're gonna outperform it. We do the test in kind of an equal parameter setting, even though there's some weight sharing.
And how is the symmetry like every intermediate feature representation or is it?
That's exactly right. We enforce it. You've got a big old neural network here. I think it's something like a VMAT, and each layer is enforcing this constraint. So it would seem like, well, maybe you don't have to exactly do that, but it seems like a lot of extra constraint. I think like structuring each layer of the model like that helps a lot.
What if the neural network wants to capture something where this symmetry is not valid, for example, some kind of task and everything?
Yeah. Well, then you're in trouble. We do analyze this. There's situations where this model makes it mathematically feasible to represent a desired function, and there, you know, you need to add additional representation. But there's often like this gray area where there's a model mismatch, but it's still very helpful to use this model. Yeah, if I have time, I might talk about that. Yeah.
Said that earlier, but you have a separate channel for the equivariant feature.
That's right.
So the other channel not.
No, the entire model is constrained, but in order to incorporate that constraint, we have to add extra channels to encode the group elements. All right, here we got some questions about there's different approaches to incorporating these kind of constraints into the model that are different than ours. So for example, data augmentation, another approach would be something called canonicalization. They underperform. Why do they underperform? I can hypothesize, but I don't have proof. Let me talk about, I want to talk about a little bit more before we're done here. Reinforcement learning. This is also, it helps even more on reinforcement learning. So we're learning to open a drawer here, and our model learns this very quickly, and the baseline is really struggling. This is a comparison against something from a couple of years ago, but I think this is pretty, we've got Dr. Q, we have various forms of data augmentation. This is just remarkably effective in reinforcement learning. And I think what's going on here is, as you are all probably aware, reinforcement learning does something like called bootstrapping. Small, improvements in whatever improvements we're giving you in terms of the representational power of the model are being multiplied via this bootstrapping effect. So each step of learning, we're a little bit more effective. And in reinforcement learning in particular, we're learning much, much faster. So much faster that, again, we can do RL on physical systems. Not like the most amazing tasks, but not the most ridiculous tasks either. We can, so here, the actions are 1 or 2 centimeter displacements of the hand in X, Y, Z, and theta. Again, the states are these top-down images, and this thing relatively quickly learns to perform these tasks. I want to get to this work, which is actually something we just got into core policy. So imitation learning, that's based on a diffusion model. So you guys are probably familiar. Diffusion models are generative models that have seen a lot of use in computer vision. Here we take the state as input, generally an image, and we're generating a desired trajectory. And that trajectory, this is like receding horizon control a little bit. It's a trajectory over a short period of time into the future that you'd like your robot to follow. As before, we're generating behaviors in the operational space, the Cartesian space, not in the joint space. So here, these equations are just the mechanics of the diffusion process. The thing that gets learned is something called the denoising model. The denoising model is you can think about it as the first derivative of like some kind of energy function over that you're trying to learn. The denoising function is equivariant when the policy you're trying to learn is equivariant. So here's a picture of what that denoising function looks like, and here's kind of the equivalent diagram from what we've seen before. All right, so we did this, and I won't get into some of the details, but it is surprisingly effective. So here we have this bagel baking thing. So it has to perform this big old complex task. This is trained using 58 demonstrations. So it's a lot, but it's without equivariant, you'd be doing 5 to 10 times as many demonstrations. And you would be right there in the 4th or the 5th level of hell, right above heretics. Yeah, this thing this is amazing. I was just pretty amazed when I saw how effective this thing could be. So 58 demonstrations we can get, and this is a single policy doing all of this stuff. We can get this really complex behavior out of so few demonstrations. Now, ideally, of course, we'd be doing reinforcement learning on top of this and everything. We haven't gotten there. Like all we've gotten right now is imitation learning. So I want to point out at the beginning of this thing, you can see, if you look really carefully, you can see these little green lines here. Those are the actions produced, the short time horizon action, desired action trajectories produced by the diffusion policy. So each time step we run the diffusion policy, it outputs a desired short horizon trajectory that this thing is going to follow, and that's that green line. So this thing, this video doesn't demonstrate it really well, but it's one of the things that's really cool about this, and I should have had this in the video, is failures. It recovers from failures. Just if it fails to close the oven, it's just going to try again. Maybe not super surprising. Of course, that's what we would expect a closed loop behavior to do, but it is closed loop and it totally does that. If it fails to close the little drawer, it'll go back and do that. If it fails to open or close this little the door, it can do that. If it can't pick up, it fails to pick up the bagel, it'll go back and attempt to do that. Compared to, so here's, kind of a variety of tasks done on the physical system. The baseline, the baselines are not even like without equivariance, you're not even like, it doesn't work with this number of demonstrations. So here we have the number of demonstrations. So these are not crazy tasks, and we have something like 20 demonstrations, 40 demonstrations, 60 demonstrations. A lot, but not a crazy number. And you can achieve like 80, 90%, 95% performance that way. We outperform the baselines like very, you see all these plus blue numbers. We're really outperforming here. There's a couple of different settings. There's like a voxel setting. We actually have a point cloud setting that we're not showing here. There's an image setting. It helps in all situations. These are different. These are all these mimic gen tasks. I don't know if you're familiar with these things. These are kind of baseline tasks. It works really well. And one of the things that's kind of interesting is, sometimes we have these red numbers here. It means we're underperforming. How come we're underperforming here? This is performance with 100 demonstrations, 200 demonstrations, 1,000 demonstrations.
I have a question about the evaluation phase. It's like, it's like you evaluate around different rotations. So are you training only on one rotation?
No, we train and evaluate on all different orientations. That is a good question. Yeah.
Just the demonstrations is limited.
No, they were, no, I honestly, I don't remember exactly. It could be that they demonstrated only some of the rotations and not all of them, but I believe we were demonstrating all of the rotations.
Okay.
It's the more demonstrate, when you go from the small data regime to the larger data regime, this becomes less helpful. So you have 100 demonstrations, you definitely want to be doing this. If you have 1,000 demonstrations, less clear. And there's actually some negative health effects here due to, especially in this case, the image. And the reason for that negative effect is that, first of all, we have a lot of demonstrations, so there's less need for the equivariant model. But second, there's some symmetry violations, which I've downplayed, but they're clearly here in these image-based domains because of the presence of the arm, and that impedes progress. It's generally still helpful to use this model in those situations where you have that symmetry breaking behavior, but as you get more demonstrations, the benefit is lessened.
The truth, the environment we're symmetric, there were no symmetry violations,
then you would not expect to see any. Yeah, there's usually always some kind of symmetry. Yeah, let's just talk a little bit about it. So this is actually a situation that we studied a lot, and I'm not gonna talk about it hardly at all here. But we're actually very interested in this case where you have symmetry violations. There's two types of symmetry violations that have appeared in the in situations I've shown so far. The first is the presence of the robot arm. The robot arm is a violation because when you rotate the scene, the robot arm is not rotating. It's kind of fixed there. The other symmetry violation is that these views are actually not top-down views. Most of these views are from the side. So there's kind of when you rotate that side view, it doesn't exactly match up with what an actually rotated scene would be. But the interesting thing is that it's usually the case that using the equivariant model helps. And the way I think about it is that, there's pros and cons to the equivariant model. The equivariant model, there's many benefits. It really improves learning. But if there's model mismatch between domain structure and the model structure, that can hurt things. And those two effects kind of fight each other a little bit. And until one of the really, again, surprising things that we found is that until that those harmful effects really become, insurmountable, you're generally better off using. It's generally helpful to be using the equivariant model. It's not as helpful as if you had a perfect match between model structure and domain structure, but even when don't have that perfect match, it's usually very helpful to use an equivariant model. And we have a lot of analysis to that effect that I don't have time to go into. All right, the rest of this I'm not going to talk about because it's time to go. Suffice it to say that there's additional types of we've talked about symmetry just in a single scene. Turns out you can think about bi-equivariant symmetry, like symmetry involving like multiple objects moving independently. You have amazing results in those settings as well. You can apply that in 2 dimensions or in 3 dimensions. One of the things that is really important to this line of work is a representation of orientation using Fourier functions, in particular spherical harmonics. So one of the challenges that you run into going from, you might criticize, say, well, you're only looking at finite subgroups of SO2. But it turns out these methods are applicable to the continuous space, SO2 space. Even to SO3, the mechanism used to get there is, again, it's a discretization, but it's a discretization in terms of the harmonics of a spherical function or an SO3 function. So you can decompose, you can write a function over the sphere using these spherical harmonics, and and it's a continuous function, but you represent it in terms of a finite number of parameters. So we recently used this work in some grasping work where you basically input a voxel, a point cloud, I don't know. You're inputting some voxels and point clouds, and each one of those voxels is outputting a spherical signal, which is telling you not only how good is the grasp location, but what should the orientation be. And because we're using the spherical signals, we're able to, incorporate our equivariant constraints into the model. Grasping is kind of a pet domain of mine, and this works better than anything else that I've ever seen. Of course, we just got this accepted at Coral, but yeah, you can, as is often the case, by incorporating equivariant models, you can outperform anything else that's out there, and that, again, that's the case with grasping. These are results of simulation. Here are some results on the physical system. These are, it's like, why are you doing this particular type? These are just kind of benchmark type grasp scenarios. This is a so-called pile scenario where stuff gets just jumbled together, and the pack scenarios where you put stuff up right and you try to jam it together so it's hard to pick up. This is just to my knowledge, this is the best you can do with grasping in terms of just the model stuff. All right, talk over. Lunchtime, time to get back to that ICRA paper. The message, I just have a couple of messages for you. Number one, equivariance really helps on a variety of problems, whether it's imitation learning, reinforcement learning, even some grasping. And second, you too can benefit from this amazing thing. So that, there's libraries, they're not that hard to use. It helps if you have some background in abstract algebra, but it's not absolutely essential. It's often the case that whatever model you have, you can identify structure, incorporate equivariance into the right parts of the model, and it will just get better. Great. Thanks.
But some time for questions. Yeah, perfect.
The intuition you gave in the beginning was that we rotate these domains.
Yeah.
And so we're trying to enforce rotation invariance. But then when you showed, like, I think you said canonicalization, which, was sort of my naive view of how to do that.
Yeah,
Just transform the state
That's
space.
great. That's right. Transform
Right,
the
so-
state space and like canonicalize both the state,
Yeah.
Yeah, like, it's like you rectify the state space with a particular orientation, and then you
Right.
do your reasoning in that, and then you derotate the other stuff.
So, yeah, I'm having some trouble like squaring that intuition with the results I'm seeing, because I would think that would take care of the entire problem. And then in addition, I guess,
Well, let me try to answer that question. I think that a lot of the benefit has to do with the additional structure in each of the neural network layers. So yeah, then, you can say, you're reducing the size of your learning problem. I get that by doing canonicalization, but you're not doing anything with the model. So our model has fewer parameters and it's generalizing more effectively in a way that an unconstrained model
at
would not.
each layer beyond the first one.
At each
seems
layer,
to be
yeah.
Counterintuitive to the intuition you gave, right? Because if I snap that domain to a canonical state space, then what is there left to do to get the, I believe that extra structure changes the learning, how fast this thing
Yeah.
can learn. But it just feels like something else is going on than just being sort of invariant to geometric rotations. Did you just do it on the first layer and try it, after that? Let every other layer beyond that go? Like, that seems like.
Well, right, okay, so, yeah, I don't know, maybe you would do this in one layer and you'd convert to to an invariant representation, then everything after that would be standard. That was what you're saying.
Right, yeah, I mean, because it just seems like this is only present in the first layer, this variation that you're interested in sort of removing.
Well, I mean, it doesn't have, like, I think what you're saying seems like a perfectly valid model. So you could, you could make your model like invariant to rotation in that first layer. I think it's more effective to not do that, so in my simple example, I said that we introduced an additional channel that corresponded to, in the case of the finite group, like each of the finite elements of that group. And that structure, those elements kind of carry through the entire model. And I think that's helpful. Like it's instead of projecting to an invariant representation, it's keeping all of that throughout the model. It's like keeping information about all four rotations through the model or something. Yeah, I don't have a really succinct answer, unfortunately. It's
yeah, you have the results. I just want the intuition for
Yeah.
the deeper layer, but
I like the best I think I can do is to say that each layer of the model is more structured and there's fewer parameters, even compared to the to the canonicalized setting that you're talking about. Yeah. I think I'm pretty sympathetic to where you're coming from though. Other question? Yeah.
I have a question about your symmetry choice. It seems like you're using a single symmetry state space or single symmetry operator per task. Have you looked at making that flexible, having different paths that the model can go down and sort of learn for itself?
I like that idea. We haven't done nearly enough in that direction. The thing that we have done, and actually not myself, my collaborator Robin, without me, has done work looking at approximate symmetries, where essentially you'd have a constrained part of the model, you have an unconstrained part of the model, and they're some combination. So you try to get the unconstrained model would give you the ability to kind of move outside of that symmetry constraint while still benefit. So that's helpful, but that's not quite the same. One thing that maybe you'd like to do is get some experiences in a particular domain, identify what kind of structure exists in that domain, use it to structure subsequent downstream level. Yeah, and we haven't done it. We said we should. You should. Someone should.
All right, let's see if we have last question. Okay, nothing online, nothing in person. So yeah, all right, let's thank Robert.